Good afternoon, and welcome to Black and Gold Day at Home. I'm pleased that you've joined us for an interactive hour of solving mathematical and computational problems, hosted by myself and a couple of colleagues from the Center for Education in Mathematics and Computing. This session is intended for elementary and middle school age students and their families, but all ages and abilities are welcome to participate. My name is Ian Vanderberg, and I'm a faculty member here in the Faculty of Mathematics and the director of the Center for Education in Mathematics and Computing, the CEMC. The CEMC is the outreach arm of the Faculty of Mathematics, and we've been working for more than 50 years to support K-12 mathematics and computing education across Ontario, across Canada, and around the world. We're really excited this afternoon to have alumni, friends, faculty, and students dialing in from everywhere. This is a really amazing community to be part of. Over the next hour, we're going to dive in and solve some mathematics problems. I have two colleagues who I'll introduce in a second. My colleague, Sarah, is going to present a problem, and then Christine, and then I will wrap up. In each of these cases, we'll start with some explanation of the problem, tell you what the problem is about, and give you some time to think about the problem and to try to answer it. Remember, mathematics is not a spectator sport. Don't just sit there, try something. Luckily, you might be there in your house, you might be with your family. Give the questions a try. All ages are welcome. Like hockey, like the piano, mathematics is a discipline that we get better at by practice. As we go through these problems, a few things may happen. First of all, you may get stuck. Great. You might not think that's so great, but it actually is great. Talk to someone, think some more, try a different approach. We get better at mathematics and get better at other things by getting stuck and then by getting unstuck. If you get through the problem we're doing quickly, that's great too. Ask yourself a different question. See if you can guess what the next question might be. See if you can try something harder. If you want to ask a question or answer a question, try putting that in the chat in the platform you're in right now. However, don't look at the chat if you don't want to know the answers. Again, in mathematics, it's not so good for other people to give us the answers. It's better when we try to figure this out. I would like to remind our attendees that you'll be muted throughout the panel, but the typed questions can be submitted through the Profound Impact platform. Please send in any questions that you have and we'll do our best to respond to them. If you have issues with sound or video, please use the chat function and our team will assist you. And now I'd like to introduce two of my colleagues from the CEMC, Sarah Chan and Christine Vender. Both Sarah and Christine were high school teachers before they came to the CEMC, and we've been really, really lucky to have them in the CEMC. They bring their great knowledge of education, their great knowledge of mathematics and computer science, along with a passion for education, for the importance of problem solving and the importance of these disciplines in the world. They're going to each walk you through a problem, first Sarah and then Christine, and I'm going to actually work through these problems with my 9-year-old who's sitting here with me, and then we'll be back to see you. I'll be back to talk to you at the very end. So I'm going to turn things over to Sarah now.
Hello, everybody, and a special hello to any kids who are watching today. Now, I want to tell you about something very interesting that happened to me this morning. My best friend sent me a secret message, but I'm not actually sure what it says. I'm hoping that you can help me figure it out. So I'm going to put it up on the screen so that you can all see it. So this is the message that my friend sent me. Square, star, star, square, triangle, star, square, star, triangle, triangle, triangle. Well, to change these symbols into letters, I'm going to have to do some decoding. And in order to decode, I'm going to have to know what key my friend used. The key is sort of like the map or the rules that tell me how the symbols and the letters are going to be related to each other. So here is my friend's key. This type of key is sometimes called a tree because it looks a little bit like a tree if you turn a tree upside down. The circle at the very top is called the root. So right here, I would call that the root of my tree. And extending from the root, we have all kinds of branches, and the branches are all labeled using those weird symbols. At the very tips of the branches are letters, and we call those locations the leaves, of course. So to decode our secret message, what we're going to have to do is start at the very root of the tree and follow the branches that match the symbols from our message until we reach a letter. So starting at the root, I'm going to first follow the branch labeled with a square because that was the first symbol in my secret message. Then I'm going to follow the branch labeled with a star and a branch labeled with a star, and I end up at the letter B. So this tells me that the first 3 symbols in my secret message represent the letter B. Can you work out what the rest of the letters in this message are? So let's see. To get the next letter, I'll have to go all the way back to the root. And I'll follow the branch labeled with a square. And then the branch labeled with a triangle. And I get to the letter E. The next letter is an E. Wonder what it says. Let's go back up to the root. And starting at the root, I'll follow the branch labeled with a star, and I get to the letter A. So the star here, it represents the letter A. Now, what does the rest of this message say? Oh, I see some help popping up in the chat. Thank you. I go back to the root. I'm going to follow the branch labeled with a square, follow the branch labeled with a star, follow a branch labeled with a triangle, and I've got to the letter C. I think I know what this word might be. Yes, I can see a lot of people are typing beach into the chat. I think you're right. I don't know many other words that have those letters in them, but let's see. If I go back to the root and I follow the branch labeled with a triangle and another triangle, yes, I get the letter H. Wow, this is cool. My friend is inviting me to go to the beach. I'm gonna have to send her a response. Well, I think going to the beach is a fabulous idea. So I'm gonna send the word fab back to my friend as my response. And I'm going to do it using the same code and the same key. Now to change my letters back into those symbols, I'm going to do a process called encoding. And in order to encode, I'm going to use that exact same key. So here is the key again. And to encode the message, I'm going to work one letter at a time. Again, I'm going to start at the root and I'm going to follow the branches that lead to my letter. And the symbols that I pass along the way are the symbols that I'm going to replace my letter with. So the first letter in my message is the letter F. So I'm going to start at the root and I'm going to follow branches that lead me all the way to the letter F. And the symbols that I passed along the way were a triangle and a star. So instead of the letter F, I can send to my friend a triangle and a star. Can you work out what the rest of the symbols will be? You can type those in the chat as well. Now to do the next letter, I need to go back to the root. Starting at the root, I now want to encode the letter A, so I'll follow the branches that take me to the letter A. And along the way, I passed a star. So the next symbol I'm going to send to my friend is a star. Okay. And now I've just got one letter left to do, the letter B. So again, I'll go back to the root. I'll take a look. Where is the letter B? Oh, it's down there on the left. So I'll start at the root and I'll follow the branches that take me all the way to the letter B. keeping track of the symbols that I pass along the way. So I passed a square, a star, and a star. So instead of the letter B, I'm going to send a square, a star, and a star. So that's how I can send my response back to my friend. I can send the word fab, but I can send it using our secret code by sending a triangle, star, star, square, star, and star. Thank you so much for your help with these secret messages. I really appreciate it. Oh, except, darn, I just remembered something. I actually can't go to the beach because I have to go to work. Ugh. And I work at the CEMC. How can I send my friend the message CEMC to tell her that I need to go to work instead of going to the beach? I can send a C and I can send an E, but there's no M in our tree right now. Well, one thing I can do is I can make my tree bigger by somehow adding the letter M in here. But where exactly in the tree should it go? If you have any suggestions for me on where I could put this new letter M, I'd love to hear them. You can put them in the chat. Let's see, let's think about it. There's quite a few places where it could go. One option I could try is I could maybe add another branch over here. It looks like there's lots of space on this side of the tree. So maybe I'll add another branch over here coming from the A, and I'll label it with a star. And this branch could go to the letter M. And this is one possibility of how I could add the letter M to my key. Oh, but I think I'm gonna have a problem now. My problem is gonna be this. What would happen if a secret message had 2 stars in it? Is that going to be the letter M? Or is that going to be 2 A's? That's ambiguous, isn't it? 2 stars, I can't tell if it's the letter M or if it's 2 A's. So this is a problem. I actually am not going to be able to add the letter M over here. And the reason why this is a problem is you may remember that I mentioned all the letters have to be leaves of this upside down tree. And what I've drawn right now, A is actually not a leaf anymore. It's in the middle of the branches. So this doesn't work. When we have letters here that are no longer leaves, we can get these ambiguous answers. So unfortunately, I'm not going to be able to put the M in that exact spot. Other suggestions in the chat? I see a few. Keep them coming. Let's see, anywhere in between the B and the C, okay, could go there. I like the idea of putting it there. I want to explore a few other places first before I go there. I'm wondering if I can just stick it sort of right here. What if I put my letter M there and I'll put a branch here coming from the root and I'll label it with a triangle. I wonder if this could work. Well, actually, this causes a problem too if we receive the secret message triangle star. If we receive the message triangle star, that could be the letter F. Do we see that? But it could also maybe be an M and an A. Yes, I'm seeing in the chat, people are suggesting I can put it anywhere as long as I make it a leaf. So where I have it right now, it actually is a leaf, but it's still causing some problems. What's happening here to cause this problem is we have 2 branches with the same label. You'll notice from the root that I have 2 branches coming out of it, and they both have a triangle on it. And so when we're trying to encode and decode our messages, it's not clear which branch we should follow with the triangle, okay? So you're right that the M does need to be a leaf, but it can't just be any leaf. We have to be very careful about where we put it. Okay, now I want to go back to another suggestion I saw in the chat, and that was to put it in between B and C. So let's see what happens if we do that. Okay. So what if we put the M here in between the B and C, and the suggestion was to label it with a square. We're gonna have to do that because the star and the triangle are already taken, right? So we'll put it here and we'll label it with a square. That actually would work really well. This is a good place to add that letter M. M is a leaf on the tree, and all of the other letters are still leaves. We haven't changed anything there. And we don't have any duplicate branches. We only have one branch per symbol. So that's actually a good place to put it. There are other places you could put the letter M. There is more than one right answer here, but I think that this is a good and an obvious choice. Well, thank you very much for all that help, you guys. You now have the skills to create your own cool codes. So what you can do following this session is you can choose some symbols and you can create your own tree. And you could practice sending and receiving secret messages with your friends and with your family members. I hope that you enjoyed learning about secret messages, and I hope you enjoyed learning about trees, especially the upside down kind. Thank you very much for your attention. I'm going to pass things over now to my colleague, Christine Vender, and she's got a game that she would like to play with you.
Hi everyone, I'm Christine, and today we are going to play a game called 5 Square. So I'm just going to share my screen so that we can all look at the game board together. Okay, so 5 Square is an easy game to play. You just need 2 people, a grid with 5 squares, and matching game pieces for each person. Today I'll use X's and O's as the game pieces, but you could really use anything, coins, paper clips, even small pieces of paper. So to play 5 Square, you're going to start by deciding which player will go first. And then on each turn, a player can either put one of their game pieces on one empty square or put 2 of their game pieces on 2 empty squares, as long as the 2 empty squares are right next to each other. Then the player to put their game piece on the last empty square wins the game. Now I should just point out that you'll notice I've numbered the 5 squares on my grid. That's just to make it easier for me to talk about the squares with you today. But when you're actually playing the game, you don't need to number the squares. Now I'll walk you through a game so that you can get a better feel for how it's played, and then we can talk about it a bit more. So the first player can put 1 game piece on any of the 5 squares, remember, or 2 game pieces on any 2 squares that are next to each other. So like squares 1 and 2, square 2 and 3, 3 and 4, or 4 and 5. Suppose the first player puts 1 game piece on square 2. Now I'll let that player be X. Now it's the other player's turn. The second player can put 1 game piece on any of the 4 empty squares, or they could put 2 game pieces on squares 3 and 4, or squares 4 and 5 because they're right next to each other. Suppose the second player puts 2 game pieces on squares 4 and 5. We'll let this player be O. Now it's the first player's turn again. The first player is left with 2 empty squares, square 1 and square 3. Because the empty squares are not next to each other, the first player can't cover both squares in a single turn, so they'll need to pick 1 square. Suppose the first player puts their game piece on square 3. Now it's the second player's turn again. The second player will put their game piece on the last empty square, so that's square 1, and that player will win the game. Okay, so now that you have a better feel for the game, I'll give you some time to play the game either by yourself or with someone you're with, because it's going to make a lot more sense if you can have a chance to just play the game yourself. As you're playing, try to come up with a strategy that will allow you to win most of the time. Can you find a strategy that allows you to win every time? Does it matter who goes first? Think about all of these things as you're playing. I'll give you a minute or 2 to play the game and think of your strategies. Okay, hopefully you have come up with some strategies for this game. If you were able to come up with a strategy that allowed you to win every time, please put it in the chat so we can see it. Type the square number or numbers for the first move. In the meantime, let's look at some strategies together. So suppose your opponent starts by placing 2 game pieces on squares 1 and 2. Now, what would be your best move? Well, if we put 2 game pieces on, then our opponent would be left with 1 empty square and would automatically win the game. We don't want to do that. Similarly, if we put 1 game piece on square 3, our opponent could put 2 game pieces on squares 4 and 5 and win the game. We don't want to do that either. However, if we put 1 game piece on square 4, we would leave our opponent with 2 empty squares that are not next to each other. This is good because they would be forced to pick 1 square. Then we could take the last square and win the game. So strategies like this can help you win the game. But it turns out that this game does have a winning strategy. So that means that there is a strategy that allows you to always win, regardless of what the other player does. And I can see in the chat that I think someone got the winning strategy. So someone says the first person should start at 3, and that's exactly it. So for the winning strategy, we go first and place our game piece on square 3. Now let's look at why this is the winning strategy. So from here, our opponent has 2 choices. They can either place 2 game pieces or 1 game piece. If they choose 2 game pieces, then they could place them on squares 1 and 2 or 4 and 5. If they place them on squares 1 and 2, like this, then on our turn, we could just put our game pieces on squares 4 and 5 and win. Similarly, if they put their game pieces on squares 4 and 5, then we could put our game pieces on squares 1 and 2 and win. Now, what if instead of putting 2 game pieces, they chose to put 1 game piece? Well, if they chose 1 game piece, then they can place it on square 1, 2, 4, or 5. If they put their game piece on square 1 or square 2, then we would put our game piece on square 4 or square 5. So we would go on the other side. Then you see that we've left them with 2 empty squares that are not next to each other. So they would take one of those empty squares and we would take the last one and win the game. Now you can see it doesn't matter if they chose square 1 or square 2. It doesn't matter if we choose square 4 or square 5. The key is just that we want to go on the other side of the grid. Similarly, if they put their 1 game piece on square 4 or square 5, we would go on the other side and put it on square 1 or 2. You see, it doesn't matter which one. Then we're still leaving them with 2 empty squares that are not next to each other. They would take one, we would take the other, and we would win the game. So either way, we can win the game regardless of what our opponent does. That makes this a winning strategy. Now, you might be wondering, is there another winning strategy? So to figure this out, let's consider all the possible first moves that the first player could make, and then explore what could happen next in the game. We want to see if there's another first move that can guarantee a win for the first player. So let's be systematic about this. We'll start with the first move of square 1. So if we put 1 game piece in square 1, well, let's think. Well, our opponent could put 2 game pieces in squares 3 and square 4, and oof, that wouldn't be good, because then we're left with 2 squares that are not next to each other. We need to pick one, our opponent would take the other, and they would win. So that's not a winning strategy. And similarly, choosing square 5 would not be a winning strategy because that's just, the game flipped around. If we chose square 5, our opponent could choose squares 2 and 3 and win the game. So neither of those would be winning strategies. Okay, let's keep a record here. So not square 1, not square 5. Okay, let's try square 2. Okay, Okay, if we start with square 2, then let's think about this. Oh no, our opponent could go in square 3 and in square 4. If they did that, then we're left with 2 empty squares that are not next to each other. We would need to pick one, our opponent would need to pick the other, and they would win. So this is not a winning strategy. Similarly, if you just look at this flipped over, if we went in square 4 as our first move, then our opponent could just put their pieces in squares 2 and 3 and win the game. So that is also not a winning strategy. Okay, so let's keep a record here. Not square 2, not square 4. Square 3 we already talked about. Square 3 was the winning strategy. So those are the 5 possible first moves if we put only one piece down. What if we put 2 pieces down? Let's say we do square 1 and square 2. Well, our opponent can just go in square 4, can't they? Leave us with 2 empty squares that are not next to each other. We take one, they take the other, they win. So that's not a winning strategy either. And then if you just look at this flipped over, the same thing applies if we go in squares 4 and square 5, because then our opponent can just go in square 2 and win the game. Okay, so those are not winning strategies either. Let's add those to our list then. Okay, what if we do square 2 and square 3? Let's try that. Well, our opponent could just put their piece in square 4, couldn't they? And then that would leave us with 2 empty squares that are not next to each other. We take one, they take the other, they win. So that's not a winning strategy either. Similarly, if we put our pieces in squares 3 and square 4, that's just kind of the flipped over version of this. Our opponent could put their game piece in square 2 and win the game. So that's also not a winning strategy. So let's add those to our list and take a look here. So not square 2 and 3, not square 3 and 4. Well, that's it. Those are all the possible first moves. And the only one that guaranteed the first player a win was to put one game piece on square 3. So that means it's the only winning strategy. Now you might be wondering, is there a winning strategy for the second player? So we have seen that it is definitely possible for the second player to win the game, especially if the first player does not start by putting one game piece on square 3. However, because the success of the second player depends on what the first player does, we can't call this a winning strategy because a winning strategy allows you to win regardless of what the other player does. So the only winning strategy for this game is for the first player to start by placing one game piece on square 3. Now, we don't need to stop here. We can keep this game going. If we add another square, we could call this game 6 square. We would keep the rules the same, but do you think the strategy changes? Let's find out. Let's think about this. So our strategy for 5 square was to put our first game piece on square 3. This was the winning strategy for 5 square. So let's think about if this is still the winning strategy for 6 square. And while we're thinking about that, there's a couple questions in the chat that I can talk about. Someone asked, what if you both win? Well, you can't both win because the winner is the person who puts their game piece on the last empty square. So actually only one person is able to win this game. Another question is if all these games are on the CEMC website. Yes, this game actually was part of CEMC at Home, which was a set of resources that we created in the spring. This is part of the grade 7-8 collection of resources. So you can find it all online with CEMC at Home. And if you like games like this, there's lots more logic style games like this that you can explore through CEMC at Home activities and just on their website as well. So thinking back to 6 square, if this was the first move, for the second move, we could just place a game piece on square 4, couldn't we? And I think someone mentioned this in the chat too. Because if you do this, this looks a little familiar, doesn't it? This looks, we've got 4 empty squares, 2 on either side. This looked like what the grid looked like after the first move in the winning strategy of 5 square. So that means that the second player can win this game. So the winning strategy for 5 square is not the same as the winning strategy for 6 square. So it turns out there's actually 3 winning strategies for 6 square. So one of them I've kind of alluded to here. So one of the winning strategies would be to start by placing 2 game pieces in squares 3 and 4, but there's actually 2 other winning strategies, but I will leave it up to you to find the other 2 strategies. And then once you've done that, you can move on to 7 square, 8 square, 9 square. I mean, keep going. Do you think that you'll ever end up with a game that has no winning strategy? There's so many things you can explore with this game, and I encourage you to see what you can find. Now, that's all the time I have for you today. So now I'm going to pass you over to Ian, and he's going to do a math problem with you.
I hope you've all had lots of fun so far solving these problems. They've been really interesting. My 9-year-old and I have been working feverishly through them for the last half hour. Before we come to the problem that I'm going to do with you, I just want to mention a couple of quick things about some connections with the problems that Sarah and Christine have talked about. These problems, like many math problems, are lots of fun to play around with and try to solve. And the question some people sometimes ask is this really like math in the real world? Can I get a job that just involves playing games and trying to win them? Well, yes and no, I think the answer is. The problems that Sarah and Christine have done are both really relevant to things that do happen in the real world. So Sarah's problem with the code is related to the study of languages and the study of cryptography. So both of these are really important things. Cryptography is how we turn things into code to make, for example, the internet secure. And that relates to what Sarah has talked about, as well as the study of computer languages and languages in general. Christine's problem, where she talked about strategies and how to win a game, again, it seems like a fun thing to do. And now that you know the winning strategy, you can play with your older brothers and sisters and they'll never have a chance to win. This might be your one and only chance to do that, so go for it later on. But game theory is a really important area of mathematics that is really useful in areas like economics and biology and other parts as well. So it's really worth exploring some of these. And lots of the things that we use in mathematics really are about training our brains to think. Mathematics exists for fun, because there are lots of fun things and lots of important things that help build the world around us. But also it's a discipline that helps us learn how to think logically, to think systematically, and to try to solve problems. And lots of the problems that we have information that we're given and information that we want to try to find out. In Sarah's problem, we were given the tree, we were given the code, and we wanted to solve that. In Christine's problem, we had a game, we had some setup, and we wanted to solve that. I'm now going to show us a problem here. So I want to talk about maps. Do you like maps? I know my 2 boys do, and you can see one of them here studying the map of Ontario, and there's Kitchener-Waterloo down on the right side. Many maps have on them a distance chart. So if you look inside the map somewhere, you might find near the back of the book or on one side of the map, you might see a chart that measures the distances between various cities. It's kind of interesting to look at this and figure out how far you are away from various places. Those of us of a certain age who grew up in Ontario might very well remember having road maps in our car that we had to, in our parents' cars, that we had to fold up and unfold, and you might have spent hours trying to fold and unfold those maps. We're going to do a problem now that involves distances and a map. Now, like many things, when we solve mathematics problems, sometimes we need to simplify in order to figure out how to do this really well. So I'm going to simplify and look at 4 towns that lie in an order along a straight road. Now again, for those of you who may have spent time in Kitchener-Waterloo, and many of you who are alumni of the University of Waterloo will remember, there are no straight roads in Kitchener-Waterloo. So do not think of Waterloo as an example. Think of another favorite place that has straight roads in it. So consider 4 towns, and we're going to call them W, X, Y, and Z. If you want to come up with names for them, that's great. We're told that the distance from W to X is 27 kilometers, and you can see that labeled on the diagram. The distance from X to Y is, the distance from X to Y is 21 kilometers, and the distance from Y to Z is 19 kilometers. So the question is, can we find distances between other pairs of towns? Well, we can find the distance from W to Y by adding the distances from W to X and X to Y. When we add 27 and 21, we get 48 kilometers. Can we find the distance from X to Z or the distance from W to Z? Take a couple of minutes and see if you can figure out those distances, the distance from X to Z and the distance from W to Z. Hopefully you've looked at this and you can see what these distances are. To get the distance from X to Z, we add the distances from X to Y and Y to Z. And that gives us a total of 40 kilometers. To get the distance from W to Z, we add all three of these distances together, W to X, X to Y, Y to Z. And we add these, we get 67 kilometers. Is there another way we could have gotten that total distance? In fact, there is. We already knew the distance from W to Y, and we knew the distance from Y to Z, so we could have added those two together. We could have added 48 and 19 to get 67. So there's our problem number one, and I'm going to put all of this information in a chart. So you can see the map, you can see the two questions we've asked, you can see a chart down at the bottom right, which looks at the distances. So if you look in the column for W and the row for X, you see a 27. That's the distance from W to X. You can see the distances from X to Y and Y to Z there already. We've put in the distance from W to Y that we calculated, and now we can add in the other two distances. So this one is not too bad. We take some information, we're given 3 pieces of information, and we're able to get 3 pieces of information out. We had the 3 shortest lengths, and we were able to use those to come up with the 3 longer lengths. Now that we've done that, I think we're ready for something a little bit more intricate. So now let's suppose that we've got 5 towns, P, Q, R, S, and T, lying in that order along a different road. The first question that I'd like you to think about, and I'll give you a few seconds to think about this, is how many pairs of towns are there? How many distances are involved? So in the previous problem, there were 4 towns, and there were in fact 6 distances. W to X, W to Y, W to Z, X to Y, X to Z, and Y to Z. Can we now find in this next problem how many pairs there are? Think about this. So it turns out there are 10 possible pairs of towns, and I'm going to list them down here on the screen. One really good way to do this is think about this really systematically. Start at P. I'm going to go from P to Q, then P to R, then P to S, then P to Z. That's 4 distances, 4 pairs. Then I start at Q. I don't have to go back to P, so I keep going forward. Q to R, Q to S, Q to T, that's 3 more. R to S, R to T, and S to T. And that's 10 distances in total. So now let's imagine that I'm given some pieces of information. I'm given 4 pieces of information here. I'm told that the distance from P to R is 29. Look in the column from P and the row from R, and I get 29. Now look, I'm also given the distance from P to S. P to S is 48 kilometers. I'm given the distances from Q to S as well, and R to T. So I'm given 4 of the 10 distances. I know 4 things and I want to figure out 6 things. The question is, can I figure those out? This is a little bit trickier here because I'm not given any of the shortest distances. I don't know the distance from P to Q, or Q to R, or R to S, or S to T, but now I need to figure out some information. What I would suggest you do, and I'm going to give you a couple of minutes to try this, draw this out on a piece of paper, or draw it out in your head. Try to label some of the distances like we labeled them earlier on with bars underneath the map. So label the distance from P to R and P to S, and see if some combination of addition or subtraction or both might let you figure out the distances from R to S, one of the underlined ones in the chart, and from P to T, one of the other underlined ones in the chart. I'll give you a couple of minutes to try to figure this out now. If you figure those out, try to figure out some of the remaining lengths as well. So let's figure this out now. Let's look first of all at R to S. We know that the distance from P to S is 48 kilometers. That's one of the pieces of information we're told in the chart. And we also know that the distance from P to R is 29 kilometers. So imagine you're getting in your car and you're driving from P to S, but through R. When I start at P and I drive to R, I've already gone 29 kilometers. When I get to S, I've gone 48 kilometers in total. So what's the distance from R to S? Well, it's 29 from P to R and 48 from P to S. So from R to S, it must be 48 minus 29, which is 19. 19 kilometers we put in the chart right here, in the spot labeled for the distance from R to S. How about now the distance from P to T? From P to T, let's think about this again. Let's imagine going for a drive. One way to get from P to T is to drive from P to R and then to drive from R to T. The distance from P to R is 29 kilometers, and the distance from R to T is also 29 kilometers. That's a coincidence in this case. 29 kilometers first to R, and then another 29 kilometers to T. 29 plus 29 kilometers is 58 kilometers. 58 kilometers gets us all the way from P to T. Did that help? See now if you can try to fill in some of the remaining information. Can you figure out the distance from S to T? Can you figure out the distance from Q to T, from Q to R, and from P to Q? I'm going to give you a couple more minutes to try this. Maybe these ideas of addition and subtraction might work. As a hint, to get the distance from S to T, try subtracting two numbers. Maybe there are a couple of different things you could do. Give this a try. Try S to T first and then work maybe left and up in the grid to see what you can get. So let's think about this. I'm not going to finish solving this problem, but I'll point you to where you can go to have a look to find the rest of the details. Let's look at S to T. Did you find a way of figuring out the distance from S to T? Maybe you use the distances from R to T and R to S. R to T is 29 kilometers and R to S is 19 kilometers. 29 minus 19 is 10. And I see that appearing in the chat. Well done. You might also notice that 58 minus 48 is 10. Do you think that's a coincidence? I had two 29s. That was a coincidence. The 58 minus 48? That's no coincidence here. 58 is from P to T. That's the whole length of the road. 48 is from P to S. So 58 minus 48 is 10. And that's the length from S to T. I wonder, using that length, the length from Q to S is 31. The length from S to T is 10. Can you figure out the distance from Q to T? Think about that. I'm going to show you the answer now. We're going to fill this in. The distance from Q to T is 41. The distance from Q to R is 12, and the distance from P to Q is 17. Maybe you had time to figure those out, and maybe you didn't. If you're not sure if you want to try this some more, I would recommend you go and look at the CEMC at-home resources that Christine mentioned. If you go to Google and you look for CEMC at home and you type in the name of this problem, which is Roadmaps to Success, Roadmaps to Success, you'll find the problem and CEMC at home, and you can read the solution. You can try this some more. I do want to share one more challenging version of this question for you to think about. This is in that resource if you go and look for it. And then I'm going to share a couple of remarks as we wrap up. Here is the same kind of setup, a road with 5 towns on it, and four distances given in the map. However, in this case, it's actually impossible for these 4 distances to be correct. The question is, why is that impossible? What is wrong with the distances here? I'm given P to Q is 28, P to R is 102, Q to T is 200, and R to T is 125. You might wonder, what could make those distances impossible? What makes them inconsistent? There is, in fact, lots of mathematics going on underneath this problem. We've talked about using the information we were given to try to solve for unknown pieces of information. And that is one of the things that is really at the heart of mathematics. In the previous version of this problem, we were given, in the first version, in problem 1, we had 3 pieces of information, and there were 3 that we needed to find. In the second, there were 4 pieces of information with 6 missing, and we were able to find those. Maybe it seems surprising we could come up with that many. In this one, we've got 4 pieces of information, but we're told they're actually wrong, and we need to figure out why. There are lots of variations here. For those of you who remember back to your days, the alumni out there of Waterloo Math, you may remember studying linear algebra, or maybe in a high school context, you might remember something called systems of equations. These problems really relate to that, but there's lots of really accessible mathematics here for younger students. In all of the problems that we've done today, the one that Sarah did, the one that Christine did, and the one that I've done here, the problems don't involve a lot of really deep mathematics, but they involve really important thinking skills. And that is really what mathematics is about. These problems show the essence of what the CEMC itself is all about. The CEMC is there for providing resources for teachers, students, and families. Some of you will have seen our math contests in the past, and maybe have children who participate in them in now. Some of you may have had a CEMC person come and visit your school. Some of you may have looked at our courseware that covers the entire Canadian mathematics curriculum from grade 7 to grade 12. Last year, as schools shut down across the country, we had an enormous spike in usage of that courseware. And we also, as Christine mentioned, launched these resources called CEMC at Home, where for 13 weeks in the spring, we daily released a resource for grade 4, 5, 6, 7, 8, 9, 10, and 11, 12, and had more than 300,000 people download those resources over the spring. All of our resources, I think, really emphasize the importance of fun with mathematics, as the problems today have done, hopefully. Mathematics is a discipline and it's a fun activity. There are lots of great things where we need to just dive in and try things and play. The CEMC also tries to do its best to emphasize the connections between mathematics and computing. And these, of course, are many of the things that the Faculty of Mathematics at Waterloo is based on. And that's one of the reasons for our great success over the years. The CEMC definitely is there to help support the curriculum through things like our courseware, and to help students and teachers and parents move beyond that, to try to increase their enjoyment, their confidence, their knowledge, and their ability in mathematics and computer science. At the end of it, though, the CEMC really does emphasize problem solving. Whether we are in STEM disciplines, in mathematics and computer science, in engineering and science, or in the arts, problem solving is part of our world. And today in 2020, more than ever, we need people who are capable problem solvers. Whether it's in areas like vaccine production, whether it's in areas like helping mitigate climate change, whether it's in areas like building quantum computers. These are all areas where problem solving is really important, and encouraging young people like all of those out there watching today to engage with mathematics, to have fun with it, to realize it's great to get stuck and to move past that. This is what mathematics is all about. Thank you to Sarah and Christine today for their wonderful problems and for sharing with us their enthusiasm and their love for mathematics. I would encourage you to visit our website, cemc.uwaterloo.ca. Have a look for all of these resources out there. Share this website on your through your social media with your friends and colleagues and relatives. Tell them about all the great things that they can find there and the wonderful ways that mathematics and computer science are indeed helping change the world. Thank you for your continued engagement and support of the Faculty of Mathematics at the University of Waterloo and with the CEMC. And I wish you all a pleasant afternoon and a great weekend. Thank you.